close your eyes and try to imagine absolute nothingness, not the darkness behind your eyelids, because darkness is a thing you perceive, not empty space, because space itself is a structure with dimensions and potential, not silence, because silence requires time to flow and ears to not hear. True nothingness means no space to be empty, no time to pass, no physical laws, no quantum fields, not even the possibility of existence. Yet here we are, atoms arranged into consciousness, pondering a universe that exploded into being 13.8 billion years ago. So what came before the first tick of the cosmic clock, and how could utter non-existence transform into everything we see, touch, and measure? This is not just a scientific puzzle. It is the deepest riddle humans have ever confronted, and the answers emerging from modern physics are stranger than any ancient creation myth. Human language evolved in a world of cause and effect. Yesterday preceded today, winter follows autumn. Your parents existed before you were born. Every sentence we construct, every thought we formulate operates within this framework of temporal sequence. When we ask what happened before the Big Bang, we are unconsciously applying this everyday logic to a situation where it may not apply. All philosopher Ludwig Wittgenstein famously said, "The limits of my language mean the limits of my world," and nowhere is this more apparent than when discussing cosmic origins. Consider how we use the word nothing in everyday speech. It means absence. You open the refrigerator and say there is nothing to eat, but of course there is air, light, the refrigerator itself, space for food. To occupy a bank account with nothing in it still exists as an account with a zero balance. Even the vacuum of outer space, which we sometimes call nothing, contains stray hydrogen atoms, cosmic radiation, dark matter, dark energy, and the very fabric of space-time itself, warped by gravity, rippling with gravitational waves. These are all somethings masquerading as nothing. True philosophical nothingness, called the void by ancient Greeks, das Nichts by Martin Heidegger, is categorically different. It means no matter, no energy, no space, no time, no physical laws, no mathematics governing behavior, no potential for anything to happen. Is the negation of existence itself, not merely the absence of particular things. The 17th century philosopher Gottfried Wilhelm Leibniz posed the primordial existential question: why is there something rather than nothing? He considered this the first question metaphysics must answer. Our brains literally cannot visualize true nothingness because visualization requires space in which to place mental images, requires time, for the act of imagining requires a conscious observer, and all of these are somethings neuroscience shows our brains construct reality through pattern recognition. We see faces in clouds, interpret random noise as voices, impose order on chaos. The concept of absolute nothing offers no pattern to recognize, no structure to grasp, is cognitively slippery, like trying to imagine a new primary color or the experience of being dead. Even physicists struggle with terminology. When cosmologists say the universe came from nothing, they mean something very specific and technical that differs enormously from philosophical nothing. They mean a quantum vacuum state, which, as we will see, is far from empty. This semantic confusion has fueled countless misunderstandings between scientists and philosophers, between atheists and theologians. The word nothing carries so much baggage that some physicists suggest abandoning it entirely in favor of more precise technical terms. The question, what was before the Big Bang, may be as meaningless as asking what is north of the North Pole. This is not a cop-out, but a profound insight about the nature of time itself. If time began with the Big Bang, then before becomes an incoherent concept. Just as north becomes meaningless at the geographic North Pole, you could travel north from anywhere on Earth until you reach 90 degrees latitude, and then the concept of north ceases to apply. Every direction from the North Pole is south. Similarly, every moment in cosmic history may point forward from the Big Bang with no possible before. This leads to a crucial realization: our intuitions about time, causality, and existence, forged by evolution to help apes find food and avoid predators, are spectacularly ill-equipped for understanding cosmic origins. What feels obviously true, that everything must have a cause, that time flows like a river, that nothing means empty, may be parochial prejudices of our limited perspective. The universe owes us no obligation to make intuitive sense. Modern physics delivers a stunning revelation: even the purest vacuum is not empty, but seethes with activity. This discovery revolutionized our understanding of nothing and opened a pathway to explain how universes might emerge without violating physical laws. The key lies in quantum mechanics, specifically the Heisenberg uncertainty principle formulated by Werner Heisenberg in 1927. The uncertainty principle states that certain pairs of properties cannot both be known precisely simultaneously. The most famous pairing is position and momentum. You cannot know exactly where a particle is and exactly how fast it is moving at the same time. This is not about measurement limitations, but reflects deep reality. Particles do not have definite positions and momenta simultaneously. Less famously, but equally important, is the energy-time uncertainty principle. Delta E times delta T is greater than or equal to h bar divided by 2, where h bar is the reduced Planck constant. What this means is staggering. For extremely brief intervals of time, delta T, the uncertainty in energy delta, it can be enormous. The universe permits violations of energy conservation, provided the violation is temporary. The smaller the time interval, the larger the energy fluctuation allowed. This is not cheating or borrowing. It is how reality fundamentally operates at quantum scales. Picture empty space, a perfect vacuum with no particles, no radiation, nothing. In classical physics, this state would remain eternally static, but quantum mechanics says no. Constantly throughout this vacuum, particle-antiparticle pairs flash into existence, borrow energy from the uncertainty principle, exist for a fleeting instant, then annihilate each other, returning the energy. A typical virtual pair might exist for 10 to the minus 21 seconds, traveling a distance smaller than an atomic nucleus, before vanishing. These are not hypothetical or metaphorical. These virtual particles have measurable effects. In 1948, Dutch physicist Hendrik Casimir predicted that if you place two uncharged metal plates extremely close together in a vacuum, the virtual particles between the plates would be restricted. Only certain wavelengths would fit, while outside the plates all wavelengths could appear. This creates an imbalance, a net pressure pushing the plates together. The Casimir effect was experimentally confirmed in 1997 and is now used in nanotechnology. The vacuum exerts measurable force because of its quantum jitter. Physicist John Wheeler visualized space-time at the smallest scales, the Planck length of 10 to the minus 35 meters, as quantum foam, a seething froth where the very geometry of space fluctuates. Virtual black holes wink in and out of existence. Wormholes briefly connect distant points. Space-time itself is turbulent at everyday scales, averaging over huge numbers of Planck volumes. This foam appears smooth, like ocean water appears continuous though made of molecules, but zoom in far enough and reality becomes grainy, probabilistic, wild. This quantum vacuum is the closest physics comes to nothing, yet it is emphatically something. It obeys laws. Quantum field theory requires the framework of space-time, contains energy. The cosmological constant, or dark energy pervading space, is vacuum energy. It has structure described by mathematics. It is not philosophical nothing, but it is the ground state of physical reality, the lowest energy configuration. But even this ground state bubbles with activity. Here is the key insight: our entire observable universe may have begun as a quantum fluctuation in such a vacuum, a rare but inevitable statistical spike, where borrowed energy briefly exceeded the threshold needed to create space-time and matter, which then, through a process called cosmic inflation, sustained itself and grew. The universe is the ultimate free lunch, as physicist Alan Guth put it, you get something from nothing not by magic, but by quantum mechanical probability combined with gravitational dynamics that we will explore next. General relativity, Albert Einstein's masterpiece published in 1915, describes gravity as the curvature of space-time. Massive objects bend the fabric of space and time, and objects follow the straightest possible paths through this curved geometry. When applied to the entire universe, general relativity predicts that if we run the cosmic movie backward, tracing galaxies back toward each other, we reach a point of infinite density and infinite curvature, a singularity where the equations break down, producing infinities and losing predictive power. This singularity is what we call the Big Bang, but singularity means the theory fails there. Physics cannot describe infinite density. Our equations literally divide by zero. Temperatures, energies, curvatures all become infinite, which is nature's way of saying you're using the wrong theory. For decades, physicists recognized this problem. General relativity works magnificently for stars, planets, galaxies, but breaks down at quantum scales near the Planck energy, where quantum effects dominate. We need a theory of quantum gravity, merging general relativity with quantum mechanics. But despite heroic efforts, string theory, loop, quantum gravity, causal set theory, no consensus theory exists yet. Stephen Hawking took a radical approach to this problem. In collaboration with James Hartle, he proposed what is called the no-boundary proposal, published in 1983. The idea uses a mathematical trick from quantum mechanics called Wick rotation, where you treat time as an imaginary number in the mathematical sense, involving the square root of -1. This sounds bizarre, but is a standard technique in quantum field theory. When you rotate time into the imaginary plane in the equations describing the very early universe, something remarkable happens. The singularity disappears. The Big Bang transforms from a sharp beginning into a smooth, rounded surface like the south pole of a sphere. Imagine walking south on Earth. At every point, you can ask what is further south and travel in that direction. But when you reach the South Pole at 90 degrees latitude, the question, what is south of here, becomes meaningless. Every direction from the South Pole is north. The pole is not a barrier or edge. It is simply a point where the coordinates become ill-defined. Similarly, Hawking proposed that asking what came before the Big Bang is meaningless because time itself has a boundary condition. At the Big Bang, in imaginary time, the universe is finite in the past direction, but has no edge, no singularity. The geometry is closed and smooth. In his words, the boundary condition of the universe is that it has no boundary. This removes the need for an initial cause or external creator. The universe is self-contained, requiring nothing outside itself to explain its existence. This is philosophically profound. If correct, it means the universe is eternal in a specific sense, not that it existed for infinite time, but that time itself is finite yet unbounded, like the surface of a sphere, which is finite in area, but has no edge, no beginning or end. You can traverse it endlessly without encountering a boundary. The question of what came before becomes as meaningless as what is north of the North Pole. Critics note that Hawking's no-boundary proposal operates in imaginary time, which is a mathematical tool, not observable reality. The connection between imaginary time and real time we experience remains unclear. Moreover, the proposal requires specific choices in the math that are not uniquely determined. Nevertheless, it represents a legitimate scientific attempt to eliminate the need for a temporal beginning, showing that our common sense notion of time having a starting point may be an illusion or approximation. In 1980, Alan Guth, then a particle physicist at MIT, proposed cosmic inflation, a modification to Big Bang theory that solved several nagging problems and became the leading paradigm for early universe cosmology. The core idea is that a tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing faster than the speed of light, driven by a special energy field called the inflating field. To understand why inflation was needed, consider the horizon problem. The cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature in all directions, about 2.7 Kelvin, varying by only 1 part in 100,000. But according to standard Big Bang Theory regions of the sky, separated by more than a couple of degrees, were never in causal contact, never close enough for light to travel between them. So how did they equilibrate to the same temperature? It is like finding two people on opposite sides of Earth wearing identical custom outfits despite never communicating. Coincidence seems unlikely. Inflation solves this elegantly. If the universe inflated exponentially from a tiny initial patch that was in thermal equilibrium, then all the regions we now see were once close together in contact, able to reach the same temperature. Then inflation stretched this tiny uniform patch to cosmic scales, carrying the uniformity with it. What appears as distant, disconnected regions today were once intimate neighbors. The flatness problem is equally puzzling. The spatial geometry of the universe is remarkably flat, meaning parallel light rays remain parallel rather than converging or diverging, but flatness is unstable. Any slight deviation from perfect flatness early on would grow exponentially. Why is the universe so precisely flat today? Inflation provides an answer. Just as inflating a balloon makes its surface appear flatter, a tiny curved patch of spacetime inflated to cosmic proportions becomes indistinguishable from flat. But the most remarkable aspect of inflation for our purposes is what drives it. The inflating field is a quantum field like the electromagnetic field or Higgs field permeating all of space. When this field sits in a high energy state called false vacuum, it creates a negative pressure or repulsive gravity. This negative pressure drives exponential expansion of space itself. As space expands, the inflating field energy density remains constant because the field is in a special state, creating more energy. As space grows, this sounds like it violates energy conservation, but in general relativity, gravitational energy is negative and can balance the positive energy of the field. The universe is the ultimate free lunch, all the positive energy in matter and radiation balanced by negative gravitational potential energy, summing to zero. Inflation typically lasted from about 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang, during which the universe expanded by a factor of at least 10 to the 26 and possibly far more. Our entire observable universe, containing hundreds of billions of galaxies, arose from a patch smaller than a proton. This almost incomprehensible expansion was driven by quantum field dynamics operating in the first moments of existence. Crucially, inflation did not need to start everywhere simultaneously. In eternal inflation scenarios proposed by Andre Linde and others, inflation continues forever in most regions of space, while occasionally stopping in small pockets. Each pocket where inflation ends becomes a bubble universe undergoing normal expansion. Each bubble is causally disconnected from others, expanding away faster than light can travel between them. Our observable universe is one such bubble. We see only our bubble. Interior, a finite region whose edge is the cosmic horizon beyond which light has not had time to reach us since our local Big Bang. Quantum fluctuations in the inflating field during inflation get stretched to cosmic scales and frozen in these fluctuations. Seed the density variations that grew into galaxies, clusters, and the cosmic web we see today. Observations of the cosmic microwave background by satellites like COBE, WMAP, and Planck have measured these fluctuations with exquisite precision, and they match inflationary predictions with stunning accuracy. The statistical pattern, the amplitude, the scale dependence all fit inflation models. This is why most cosmologists accept inflation. Despite its exotic nature, it makes testable predictions and passes tests. Inflation provides a mechanism for the universe to explode from essentially nothing. A quantum fluctuation in a pre-existing vacuum could create a tiny patch of space in the false vacuum state, which then inflates exponentially, creating vast amounts of space energy, and eventually matter. The initial energy can be arbitrarily small because inflation multiplies it. The process is probabilistic rare, but in an eternally Inflating multiverse, inevitable somewhere, somewhen. If inflation can start once, it can start infinitely many times. This realization leads to one of the most controversial ideas in modern cosmology, the multiverse and eternal inflation. Once inflation begins in any region, quantum fluctuations ensure it never completely ends everywhere. Inflation stops in some regions, producing bubble universes like ours, but continues in others. Those regions keep inflating, and within them, new bubbles form. This process has no end. Inflation is eternal into the future, and possibly eternal into the past. Physicist Andre Linda compares this to a fractal tree. Each bubble universe is a branch, and each inflating region sprouts new branches endlessly. There is no single Big Bang, but infinite Big Bangs, each creating a causally disconnected universe. The multiverse as a whole is eternal, dynamic, and infinite. We inhabit one tiny branch, unaware of countless others. String theory adds another layer. String theory attempts to unify quantum mechanics and gravity by proposing that fundamental particles are actually tiny vibrating strings. The mathematics of string theory requires extra spatial dimensions beyond our familiar three-string theory, has an enormous number of possible solutions called a landscape, estimated at 10 to the power of 500 different vacuum states each, corresponding to different physical laws, different particle masses, different force strengths, different numbers of dimensions. If eternal inflation explores this string landscape, each bubble universe could have different physical laws randomly selected from the landscape. Some universes have strong nuclear forces, others weak. Some have electrons 1,000 times heavier, others with no electrons at all. Most are sterile, lifeless, unable to form stars or chemistry. A tiny fraction have laws conducive to complexity and life we necessarily find ourselves in. One of those rare life-permitting bubbles. This is the anthropic principle. We observe the universe to be life-friendly, not because all universes are, but because we could not exist in the others. This idea frustrates many physicists because it seems to abandon the goal of explaining why our universe has the specific properties it does, replacing explanation with cosmic lottery. You won the universe lottery because countless tickets were drawn. Critics call it giving up on physics, a retreat from explanation into probability. Proponents counter that if the multiverse is real, denying it because we dislike the implications is unscientific. We follow evidence wherever it leads. Can we test the multiverse? Perhaps collisions between bubble universes could leave imprints in the cosmic microwave background, cold spots, or patterns. Some researchers claim to see hints, though most remain skeptical. Gravitational waves from the early universe might carry signatures of inflation that constrain multiverse models. The bicep experiments search for these, though definitive detection remains elusive. Statistical anomalies in the distribution of galaxies might reveal we are not in a typical region of our bubble. Some propose using quantum mechanics itself. Many world interpretation suggests branching realities akin to multiverse bubbles. Philosopher Karl Popper argued that unfalsifiable theories are not scientific. The multiverse seems unfalsifiable if other universes are forever beyond observation. But modern philosophy of science recognizes that theories are judged on multiple criteria: explanatory power, mathematical consistency, connection to established physics, ability to make any testable predictions. The multiverse arises naturally from well-tested theories: inflation, quantum mechanics, possibly string theory. It is not ad hoc, invented to explain one fact, but an unexpected consequence of pursuing other ideas. Perhaps more striking, the multiverse addresses the deepest question: why anything exists at all. In an eternal multiverse, existence is necessary, not contingent. The multiverse as a whole has no beginning and no end. Inflation ensures every possibility is realized somewhere. Nothing needs external creation or first cause. The system is self-sustaining, self-creating. The philosopher David Hume argued that while every event within the universe might need a cause. The universe as a whole need not this. Reasoning applies even more forcefully to an eternal multiverse. We began with the question, what was before the Big Bang, and discovered the question itself, maybe malformed time, likely began with our universe, making before meaningless nothing in the philosophical sense, absolute non-existence, never existed, and perhaps cannot exist. The quantum vacuum, the lowest energy state, is alive with fluctuations. Universes can and do emerge from such states, driven by probabilistic quantum processes and inflationary dynamics. Our universe is possibly one bubble in an eternal multiverse, an infinite cosmic tree with no root. What does this mean for us, for meaning, purpose, our place in existence? Some find the multiverse depressing. If every possibility occurs somewhere, do our choices matter? Is everything diluted into statistical noise? Others find it liberating. We are not cosmic accidents, but inevitable expressions of physical law. The universe is not indifferent, but fecund, endlessly creative. Our existence required no supernatural intervention, no fine-tuning, no cosmic coincidence, just patience and probability. The ancient question, why is there something rather than nothing, receives a radically new answer. There is something because nothing is unstable. The quantum vacuum cannot help but fluctuate, and rare fluctuations grow into universe's existence. Is the default nothingness, the impossibility? Philosopher Leibniz thought nothing was simpler than something, thus more probable. Physics suggests the opposite. Nothing requires perfect symmetry, perfect stillness, perfect balance. Something requires only quantum noise and time. Our universe, finely tuned for life, appears less miraculous in a multiverse. Most bubbles are dead, but some live. We are here because we must be in a life bubble. Anthropic reasoning replaces design. The multiverse is not created for us. We are a side effect of its vastness. This is humbling. We are not central, not special, one arrangement among countless others. Yet we are necessary. If laws permit life and infinite trials occur, life appears somewhere. That somewhere includes here now. Free will, causality, morality seem threatened if all outcomes occur, but physics describes possibilities, not necessities. Quantum mechanics is probabilistic, not deterministic. Even in many worlds, your choices shape which branch you experience. Morality arises from consciousness and consequence, not cosmic uniqueness. Meaning is constructed by conscious beings, not handed down from physics. Our smallness in the cosmos does not diminish love, beauty, discovery. These emerge from complexity, from the intricate dance of matter and energy in rare pockets of order. Science has not answered every question. We lack a final theory of quantum gravity. We do not know if the multiverse is real or mathematical fantasy. We do not know why the laws of physics are mathematical, why mathematics describes reality. We do not know if consciousness requires explanation beyond neurons. We do not know if our universe will end in heat death or rebirth. Mysteries remain and likely always will. But we have learned that nothing is not simple, that existence may be eternal, that our universe is possibly one note in an infinite symphony. We have learned that the deepest questions require abandoning intuition, embracing mathematics, following evidence in strange territories. We have learned that asking what was before time is like asking what is north of north, a category error born of limited perspective. The journey from ancient myth to modern cosmology is a journey from certainty to wonder and myth. The answer was simple: gods created everything, mystery solved. But science reveals layers of depth. Questions spawn questions. Each answer opens new vistas. We trade comfortable stories for uncomfortable truth. We accept that reality owes us no obligation to make sense, that our brains are limited, that understanding comes slowly through hard work and humility. Standing under the night sky, we see photons that traveled billions of years from distant galaxies, born in our cosmic bubble. We are made of atoms forged in stellar cores, scattered by supernovae, organized by chemistry, into thinking, feeling beings capable of asking where we came from. The universe has awoken to contemplate itself. In us, we are the cosmos, knowing itself. Before the Big Bang, there may have been before only timeless quantum potential waiting to fluctuate, or eternal inflation, forever budding universes, or imaginary time curving back on itself, or something we have not imagined yet the answer remains uncertain. But the quest to find it defines us. We are the species that asks why we may never know everything, but we will never stop asking, and in that restless curiosity, in that refusal to accept easy answers, in that endless reaching toward understanding, we find our deepest purpose.